Okay, hi everyone. Let us start. I want to actually leave some, I want to give some corrections and additions to a couple of previous lectures. There were just a couple of moments there where I was a little bit uncareful. So the first part is corrections and additions to previous lectures. And there will be corrections to basically two topics. The first is limit sets. And actually, the correction is in the following theorem. I said that if gamma 1, so let me formulate the theorem, and probably I will just give a proof here. So if gamma 1 is an infinite normal subgroup, if gamma 1 is an infinite normal subgroup of a non-elementary discrete group gamma 2, so it is a discrete group of isometries of the hyperbolic space HD, then their limit sets coincide, right? So this is the theorem. And I think I would like to prove it here. So first of all, we observe that since gamma 1 is a subgroup of gamma 2, right, we definitely have one inclusion. So since gamma 1 is a subgroup of gamma 2, we have that lambda gamma 1 is contained in lambda gamma 2. Why? Lambda gamma 1 is the closure of some gamma 1 orbit intersected with the boundary, right? This is definitely the subset of the closure of gamma 2, since gamma 2 is larger. Okay, I will write it here. Intersected with the boundary. And this is the limit set lambda gamma 2, right? So lambda gamma 1 is contained in lambda gamma 2. Okay, then I will use the following notation. So denote by okay, my notation is apparently pretty long, but so it's fix sub NE of gamma is the set of fixed points of non-elliptic elements, of all non-elliptic elements of gamma, right? So this is the set of all fixed points of non-elliptic elements of gamma. It's like the general notation, okay? A general notation. So there is the following lemma. First of all, lambda gamma is actually the closure. It is just the closure of this fix and E of gamma. I'm not, well, okay, I can just give a hint to proof of this theorem, right? If, first of all, let us think about these elements, right? These are parabolic or hyperbolic elements. One can just show that this set is, so this set is closed and gamma invariant. On the other hand, it definitely is contained in lambda gamma, right? So I will roughly sketch the proof here. First of all, the fixed point set of all non-elliptic elements of gamma is contained in lambda gamma, right? We already discussed that, yeah? That parabolic in hyperbolic isometries, they have the so-called attractive fixed points. They are definitely the limit points. For the hyperbolic element, for any hyperbolic element, you obtain that both attractive and repelling fixed points are they belong to this closure of the gamma orbit, right? So definitely this is true, and then the closure is also contained in lambda gamma. And for the reverse, you also should say that it's, and the closure of fix and E of gamma is closed. Okay, it is closed and gamma invariant subset in the boundary. To show that, you will need some work, but it's not that hard. Okay, then we are going to use this lemma, of course. So what I'm going to show is the following. I want to analyze the fixed point sets of non-elliptic elements, and let me say the following. First of all, I notice that gamma 1 is infinite, right? Since gamma 1 is infinite, okay, I will actually use also another lemma, which states that lambda gamma is empty if and only if gamma is elementary of elliptic type, right? If and only if gamma is elementary of elliptic type. This is already, this is probably not so simple lemma, but obviously if it consists of only elliptic, okay, all this is for discrete groups, right? So if it is a discrete group of isometries having only elliptic isometries, then it's definitely finite, right? So in fact, this so if it is elementary of elliptic type, and thus is finite, right? So I cannot, for discrete groups, I cannot have infinite gammas with empty elliptic set, right? So since gamma 1 now is infinite, right, we have that this fix and E of gamma 1 is not empty, right? If it is empty, we have only, well, we will basically have empty lambda gamma by the first part. Well, okay, more precisely, if it is empty here, right, I obtain by the first lemma the empty lambda gamma. If the lambda gamma is empty, I use the second lemma and I get that it's finite group contradiction. Gamma 1 is infinite, right? Okay, so I will say like thus we have that this is not an empty set. Okay, and this is important for us. So now let me pass to the right. So let gamma be an element of gamma 1 and G be an element of gamma 2. Then the fact that gamma x is equal to x. So if I have some point x in the space, x belongs to, okay, I wanted to write that it belongs to the boundary actually, but yeah, so if x belongs to the boundary, right, and gamma x is equal to x for some gamma, for this gamma in gamma 1, then this implies the following. I can write G gamma G inverse applied to Gx, and I simply have that it is equal to G gamma x, right? Then I use that gamma x is equal to x. So this is Gx. So G gamma G inverse has this fixed point Gx, right? So I will write, and thus Gx belongs to the set of fixed points of this conjugate G gamma G inverse. Okay, but this means that, so this means that actually the translate, right, of the fixed point. So what I took an element that belongs to the fixed point set of gamma, right? So this, and I translated by G. So I obtain something sitting in G of the fixed point set of gamma, right? And this G fixed of gamma simply is the fixed point of G. Okay, I need to be more, it's not necessarily equal, but it is a subset, right? I guess it is a subset of G gamma G inverse. Okay, but then, so yes, in this case, I obtain that, yeah, and this element is an element of, since gamma is a normal subgroup, gamma 1 is a normal subgroup of gamma 2, this is an element of, this is still an element of gamma 1, right? So I obtain that this is an element, basically this is the subset of the fixed sub and E of gamma 1, right? Since G gamma G inverse belongs to gamma 1. We recall that gamma 1 is normal subgroup of gamma 2, right? Okay, but therefore I get the following. I have that we thus obtained, right? Thus proved that the closure of, okay, we just proved that the fixed point set of gamma 1, so we just proved that x sub ne of gamma 1 is gamma 2 invariant. And actually not empty, right? Yeah.
Like fix and like are we assuming that like middle comma is not empty?
Here.
Yeah.
Yeah, the point is that this is an element of gamma 1, right? And this is not an elliptic element.
Oh.
Yeah. So this is definitely, well, it's most likely is going to be the 1 point, right? So it's just a point sitting in this subset, but we consider it as a set, so it is a subset of x and e of gamma 1. Yeah. And we just proved that it is gamma 2 invariant, right? We acted. So this thing on the left, it belongs to G multiplied by x and e of gamma 1, right? This point, this set of points over here, it belongs to G multiplied by x and e of gamma 1. So this here, I have that this is a subset of G x sub e and e of gamma 1. So eventually I obtain that x and e of gamma 1 sits in fix of gamma 1, right? So this is gamma 2 invariant. G, recall that G belongs to, it's any element from gamma 2, okay? So we just proved this. And in fact, it's, so, okay, then for a non-elementary, discrete group gamma 2, right? We have that fix sub, okay, sorry, we have the closure, of fix sub ne of gamma 1 is a non-empty closed gamma 2 invariant subset of the boundary, right? This is what we just proved. And this is important. Now we can use this theorem from the previous lectures that the limit set of gamma 2 should be thus contained in this, right? Okay, but then, so basically I can write it. Hence, we have the following. Lambda gamma 2 is contained in the closure of fix an E of gamma 1, right? Since it's a closed gamma 2 invariant non-empty subsets, which means that it contains the limit set of gamma 2. But on the other hand, by lemma, I will say like lemma 1, right? It is precisely the limit set of lambda gamma 1, right? And we already showed in the beginning that this is the subset of lambda gamma 2. So they coincide. Okay? So the fact that gamma 1 is infinite is really important, and you can try to even organize it to arrange some example, a counterexample to this theorem without this infiniteness assumption on gamma 1. So gamma 1 can be something like probably it can be something like a reflection or something, but yeah, try to think about it. Okay, so in fact, we have also some other interesting facts related to limit sets. And let me also just mention them here. I think I'm not going to prove it. I will just simply write a few statements. So there is another interesting theorem that if A is the fixed point set of all hyperbolic elements of gamma, and gamma is, I think, non-elementary, since I wanted to contain hyperbolic elements, right? So, and if gamma is non-elementary discrete subgroup of MHD, non-elementary discrete, then the lambda gamma it coincides with the closure of A. So it is in fact enough to take all hyperbolic elements sitting in the discrete group gamma. You don't need all non-elliptic, right? You can just consider a smaller subset and take its closure. Yeah, also pretty nice fact. But in fact, it can also be proved along the same lines. You just show that it is going to be closed. I mean, it's going to be closed gamma invariant subset, and then you get it. Okay. The following interesting fact is actually okay. I will write a pretty large theorem. So let me use the new board. So there is the following theorem, and we assume here let gamma be, again, a discrete non-elementary subgroup. Then we have the following. The first part, lambda gamma is actually closed with no isolated fixed, so with no isolated points, and is thus uncountable. So it is closed with no isolated points and uncountable. The second part, if there is an isometry that commutes with all elements of gamma, so if G is an isometry of HD such that G gamma equals gamma G for all gamma in gamma, then actually this is an elliptic isometry. So then G is elliptic. And in fact, our group gamma lives invariant the fixed point set of G. So gamma applied to the fixed point set of G is the fixed point set of G. So as a nice example, one can think of something like a discrete, I don't know, take a hyperplane in the space HD and take a reflection G with respect to this hyperplane, and then you can take a bunch of orthogonal hyperplanes. So it looks like a prism here, right? But I'm taking only red hyperplanes. So I have this. Then the reflection, so my gamma is generated by reflections, right? And definitely gamma R is equal to R gamma, since here I have angles being equal to pi/2, right? So these are orthogonal. This is my H, and HJ is orthogonal to H, and this gives me this commuting relation, okay? So in this case, the fixed point set is this entire hyperplane, and it is definitely invariant under the gamma action. So gamma acts, in fact, in this case, as a pretty nice cofinite discrete isometry group in the hyperplane, right? It's non-elementary. It leaves the hyperplane invariant, and we have this commuting relation. So this is a pretty nice illustration to this part 2. Okay, then the third part, the center. So it is a corollary of this. The center of gamma is finite. The center is, right, it is a subgroup of gamma, which consists of all elements that commute with everything in gamma. So definitely, since it is elliptic, it should be, it may consist only of finite order elements, right? Because of the discreteness of gamma. And part number 4. And part number 4 is somewhat related to Zariski density. So also then, if gamma leaves no proper plane invariant, no proper plane, so it is going to be some HK sitting in HD, right? So K is strictly less than D, and gamma leaves no proper plane invariant, then actually the centralizer, of gamma in G is trivial. Is trivial. I actually forgot a good notation. Probably it's, I will write here C sub G of gamma, right? Probably this is, or sometimes denoted with Z. I don't remember. So it's the set of all, what is it? It is the set of all elements in G that centralize gamma. So they should commute, right? It is G gamma equals gamma G for all gamma in gamma. So this is my centralizer. This is the set of all isometries that commute with the entire group at gamma. And well, it also follows from part number 2, right? The fixed point set of an elliptic element G is going to be some proper plane, right? If it is not, if it is not a trivial element, right? If it is not a trivial element, then it's going to be a proper plane. But if we assume that, and gamma leaves it invariant, but if gamma leaves invariant no proper plane, we are good. So part number 4 in particular covers all, so it covers all Zariski dense subgroups, right? So holds in particular for Zariski dense discrete groups. Oh, all right. Yeah. Now I want to continue my corrections and additions part. And I want to save a couple of words about Zariski dense and algebraic subgroups. So Zariski density, okay, algebraic subgroups. And Zariski density in isom HD. By the way, any questions so far? No, all good?
Yeah, so in case 2, I guess also case 3, how that lambda gamma is going to lie in this proper plane, right? Yes, okay.
Yeah. Yes. Yes, in this case, indeed. Well, it's kind of like, it's indeed. Actually, I think this is used in the proof, yeah. But the proof of part 2 is actually, I don't really remember, but as I remember, it's not really very short one. So like altogether, this is a pretty big theorem. Yeah, but it is very useful. This one is very useful. And I basically used some of these facts in some of my papers, I think. So I definitely used this fact, and I need to give some correction. So in fact, let me start with the definition. If, okay, we will say that, so we say that an isometry G from of the hyperbolic HD space, D-dimensional space, is, okay, sometimes it's called a glide or a motion. So it is a glide along a plane U in HD, if it leaves U invariant, and it acts trivially in the normal space. And so if GU is U and G acts trivially on the normal space. So we assume that RD1, right, is decomposed into the direct sum of U and its orthogonal complement. And in fact, then any actually isometry, so you can start from some plane and you can start with some isometry just sitting, well, like acting precisely in this plane, but then you can extend it to a glide in the entire hyperbolic space, right? So in particular, this means that if you have a hyperbolic, say, hyperbolic elements whose geodesic axis lie in the plane U, you do not want to have hyperbolic with twists, right, or along this, with rotations along this axis. It's not going to be a glide. But everything with trivial action on the normal space is good. But so, yeah, but I forgot that actually you can also include parabolic translations in this, right? So you can start with some parabolic element preserving some, say, circle or a sphere in this plane U, but then extend it to the trivial action on the normal complement to this U, right? And then you will get another parabolic element, which is going to be a glide along plane. So yeah, in fact, you can collect all these elements. And then the theorem that I mentioned was the following. So I wrote down this theorem, but it was a little bit, so it was, yeah, a bit wrong. We let H be an algebraic subgroup of G, where G is the isometry group of HD, be an algebraic subgroup. So like for our purposes, I obtained it as the Zariski closure of just some gamma. But anyways, it's just an algebraic subgroup. Yeah. But for our purposes, you can start with some gamma, and to check the Zariski density, you need to take its Zariski closure. It's going to be some algebraic subgroup, and then this theorem applies. Yeah. So it is an algebraic subgroup. Then its connected component, then H circle is either, so one of these two. It is either of the form G sub U times K sub U, where GU is, well, it's obviously also a connected subgroup, so it in fact contains only proper, sorry, orientation preserving glides, right? Where GU is the group of orientation preserving glides along U and Ku, K sub U is the compact group of elliptic elements fixing U, right? And the second possibility is that is a subgroup. So is either or is a subgroup of the stabilizer G sub P, where P is some point from the ideal boundary. Okay, and I will use the color to distinguish this two, to separate these two cases on the board. And this is the correct and the correct statement. So then you can apply this theorem to check that, to show that basically if gamma is Zariski dense, well, in particular, this means that it leaves no proper invariant, no proper plane invariant, then the limit set. So like basically from all these facts, it follows that the limit set is not sitting in some hypersphere of the ideal boundary. Yeah. So the conclusion was still correct. Okay, I think that yeah, but as for the limit sets, actually there are a few other facts related to Zariski dense discrete subgroups. So in particular, one can show that the normalizer of a Zariski dense discrete finitely generated discrete subgroup. Actually, I don't think you even need finitely generated. Just the normalizer of any Zariski dense discrete subgroup is also discrete. One can prove it just by using some classical methods from basically from the theory of algebraic groups, or you can show it by using this machinery with limit sets. So in this particular setting, there are several different ways, I would say several different approaches to Zariski density. Okay, yes, I think that we have some time to, I want to start, well, I basically want to move to the left board again. So I'm switching here, and my second topic is again deformations and most of rigidity. I would say deformations versus rigidity. So last time we discussed that in H2, we have deformations, right? So in H2, we have basically infinitely many surfaces. We have uncountably many, I would say, okay, lattices, uniform lattices. all isomorphic. Okay, isomorphic to some gamma G, which is an abstract group with it is a pi 1 of SG, where SG is a closed surface of genus G, where SG is a closed hyperbolic surface of genus G greater or equal than 2, right? Recall this construction with pair of pens and so on. In fact, one can notice the following. So as an abstract group remark, okay, I will start with I will probably start with the topological construction. So for any G greater or equal than 3, there is a finite cover SG to S2, right? And the construction, so it is a topological construction, not the geometric one, but definitely once you fix the geometry somewhere, you will get geometry on the other side. So let me explain it. One can take SG, and this is the so-called flower trick. So one can start we can think of this surface as being very symmetric. And so I have one pole in the middle, right? And G minus 1. So this gives me cyclic G minus 1 degree cover, right? G minus 1 degree cover. How to get this cover? I need to take the quotient by the cyclic group of order G minus 1, where the cyclic group acts simply by this rotation. So let me take the group C G minus 1, which is Z mod G minus 1 Z, right? And it acts by rotation. And this one is fixed, right? Fixed. The middle and act by rotation here. And then I obtain, sorry? Then I obtain SG over CG minus 1 is homeomorphic to S2, right? This one is fixed. And the second piece basically comes from all this coming into one equivalence class, right? Definitely, this means the following. If I have if I fix a hyperbolic metric, right, on SG, then, okay, no. If I fix a hyperbolic metric on S2, then I can find a geometric G minus D recover SG, right? Also with the hyperbolic metric, such that this now becomes a geometric cover. And for my uniform lattices, torsion-free uniform lattices in PSL to R, this means that they are all abstractly commensurable, also with 1 plus, right? So for uniform lattices, okay, for uniform lattices torsion-free, we thus have, so we have that gamma is abstractly commensurable with gamma 2, which is pi 1 of gamma 2, right? So, which means that it has a finite index subgroup. So in fact, it has a finite index subgroup, which can be realized, so, okay, abstractly isomorphic to gamma 2, yeah. So that is each such gamma has a finite index subgroup abstractly isomorphic to gamma 2.
Gamma 2, you mean sigma 2, right?
Sorry, yeah, or S2, yeah. It's a typo. Yeah, thanks. So again, we have infinitely many commensurability classes, right? In the sense of like generic commensurability classes, but we have only one commensurability class for uniform case, and in fact we have. So in fact, let me write down the statement here for non-uniform. For non-uniform torsion-free lattices, one can do actually the same thing, but with the free group. We have that gamma contains a finite index subgroup isomorphic to the free group of rank 2. And let me just remind that
So gamma will be for itself.
Okay.
So maybe like look at the quotient and then take its spine, and I have
You mean that the quotient will be free?
the quotient space will be a surface with punctures.
Yeah.
Right. So it's not compact. So
Yeah.
deformation retracts onto its spine.
Yeah.
So we're going to get a the universal cover is contractible, so this is BG, and so you're going to get a group of chronological dimension 1, which by theorem itself means it's great. Also, I mean, I think you could just explicitly sure that's the just symbols, but
Yeah, yeah, that's a nice thing.
Yeah.
Yeah, in fact, I wanted, I think I also probably something like this flower trick also might work, right? Just like arranging the punctures here, take first the quotient and then eventually obtain the once punctured cusp. Probably, oh, sorry, once punctured torus.
yes, and certain that's not going
Since F2 is just the pi1 of once punctured torus, right?
yes.
So one can probably arrange first the punctures in the center, then fix the center. I'm not sure, but yeah.
I'm not sure. I'm worried that juice to prepare
Ah,
between
yeah, I don't, yes, I don't know. Okay, yeah. Yeah, in fact, one can also work with some. Okay, yeah, we can continue with this after the break. I just wanted to remind that so this, you see, it is a bit different types of, there are different types of commensurability. So we in fact here find an abstract group sitting as a finite index. So it doesn't mean that they are all pairwise commensurable in the standard definition of commensurability. I just wanted to like compare. So I will write it here with CF, right? Bieberbach theorem. In fact, I formulated it a bit uncarefully as well. So for any lattice, for any cofinite gamma in isom ED, we have that gamma also contains a finite index subgroup, a finite index subgroup, which is ZD, right? Abstractly, isomorphic to some ZD, where this ZD is obtained for some choice of the basis in the Euclidean space. So this ZD over here is generated by some basis, for some basis in RD. So basically, you can translate along, you can scale your vectors, and you can do some, basically find deformations with them. Okay, so it means that here we have just one abstract commensurability class. Yeah. It precisely is the following, that we have just a finite index subgroup isomorphic to, so it's isomorphic to some concrete abstract group, right? So we have a finite index group, subgroup, which is isomorphic to, but this choice, it's like here, these choices of ZD acting by parallel translations, they are not pairwise isomorphic. Same here, as like, yeah, it's like with S2, right? So we discussed that we have deformations, pair of pens. So all these groups are pairwise isomorphic, abstractly, just as abstract group. But geometrically, all these are different, and their action in the hyperbolic plane is different. So they are not the same geometric groups acting in the plane, right? But they are just as isomorphic as abstract groups. So this Basically, this means that the intersection, abstract commensurability means that the intersection is of finite index without any relation to the geometry, right? You just need to find some basically isomorphism between two different groups such that the intersection gives you finite index subgroup. This is the commensurability. In our definition of commensurability, we require this isomorphism to be inherited by the conjugation by some ambient isometry of the general of the ambient space. Yeah. Okay. All right. So again, here in the Euclidean space, we have just one class, but up to the choice of the basis vectors in RD. Here we have basically two classes up to the choice of the metric on SG, right? But as abstract groups, we have two classes, either the uniform, and then they all contain finite index subgroup isomorphic to gamma 2. In the non-uniform case, they contain a finite index subgroup being a free group, the free group of rank 2. And that's it, what we have. Okay, yes, let's make a 10-minute break, maybe even 7-minute break. All right, let us continue. So, in fact, we just fixed the following picture, right? In Euclidean space, we basically have that every cofinite discrete group has a finite index subgroup that can be realized as the group of integer translations with respect to some basis, right, in the space RD, and I need the full rank isometry, translation isometry group. So, yeah, in this sense, it is abstractly commensurable to ZD. In the isometry group of H2, for lattices, we have two classes, like infinitely many standard commensurability classes, but just two abstract commensurability classes. Okay, now the question is what's going on in dimensions higher than 2. So most of rigidity theorem gives us the following. Let gamma 1 and gamma 2 be two lattices in isomage D. D is greater than 2. So let they be two torsion-free. Okay, respectively, uniform or non-uniform lattices, be torsion-free. Both uniform or non-uniform lattices, then the following is true. Then gamma 1 is isomorphic to gamma 2. If and only if, so we can view them as, right, as pi 1 of mj, sorry, pi 1 of mj, where mj is just hd mod gamma j, right? And this is definitely gamma j. It is true if and only if M1 is homotopy equivalent to M2 if and only if M1 is, sorry, actually I should start with homeomorphic to M2 if and only if M1 is isometric to M2, and if and only if there exists a G in the ambient T group of isometries such that G gamma 1 G inverse is isomorphic, well, is just equal to gamma 2, right? So in fact, this most of rigidity theorem, we will prove this theorem for non-uniform, for the case of non-uniform lattices. So we will prove it. So we will prove it in the setting of compact hyperbolic manifolds. But what I want to emphasize here, that basically generally, like in, I think that in all of these equivalences here, generally we have manifolds for which we can have like same fundamental groups, but that doesn't mean that they are a homotopy equivalent. We can have homotopy equivalent but not homeomorphic manifolds with the same fundamental groups, and so on, right? So it turns out that this rigidity is really a very strong theorem. It's a very strong statement about the behavior of compact or, well, finite volume hyperbolic manifolds in higher dimensions. Okay, what is going on in particular with abstract commensurability here? This theorem in particular implies that if we have abstract commensurability, then we have like standard geometric commensurability, right? So we do not have for every single, like say for every single lattice, uniform or non-uniform, we do not have any deformations at all, right? But we also do not have the behavior like that. So let me again, lattices in isom ED, right? Infinitely many commensurability classes, and actually even uncountably many, but one abstract commensurability class. So in isom H2, uniform, non-uniform, and here I'm writing commensurable with ZD, right? Uniform, so abstractly commensurable to pi 1 of S2. This is abstractly commensurable to F2, which is pi 1 of the torus minus the point, right? But again, large space of deformations in each setting, uniform and non-uniform. But in each class, right? But in each class, we have uncountably many really many deformations, right? And isom h d greater or equal than 3. Abstract commensurability most of implies that, right? Most of implies that abstract commensurability is the same as geometric commensurability. Means standard commensurability. And let us think again why, right? Abstract commensurability means that we have some abstract group which is isomorphic to finite index subgroups into lattices. But this means that we in fact have a geometric. Most of rigidity implies that if I took a torsion-free finite, say I have a torsion-free subgroup, right, in each of them, it means that it is realizable and there is a unique hyperbolic manifold sitting there. But then it means that I got basically this implies that I have a common finite cover, right? Geometric finite cover for more manifolds M1 and M2 if I got one abstract subgroup, right? So let me explain the picture. So if indeed, if gamma is finite index in gamma 1 and okay, it's not good. If gamma and gamma prime, right? Okay, gamma is finite index in gamma 1 and f of gamma is a finite index in gamma 2 where f of gamma to f of gamma is an isomorphism then what do I have? I have that the manifold HD mod gamma is isometric to the manifold HD of HD mod f of gamma. So then HD mod gamma is isometric to HD mod f of gamma. And this means that I have two isometric finite covers. So I have M1, right? And I have M2. And here I have HD mod gamma, which is isomorphic to HD mod f of gamma. This is my entire picture. Okay, and I have finite covers here and here. You see? So by finding like a common abstract group as finite index subgroup gives me geometric covers by HD mod gamma and HD mod f of gamma, and then most of rigidity, right? Most of rigidity is precisely this guy. Most of rigidity implies that, so this is most of rigidity. But then we look at the right part here, and it gives me that this isometry is obtained via the conjugation. So this implies that I actually have some conjugation by an element G such that G gamma 1, say G gamma 1, G inverse intersects with gamma 2 as common finite index subgroup. You see? So basically it follows from this. Right? Okay. Okay. So now the main question is how to prove this theorem. And the proof is actually, so if one tries to write down the proof with all details, it's quite complicated. The proof uses the some fundamental results of ergodic theory. And I think that in the remaining time of this lecture, I will try to write down some basic facts of ergodic actions. So let me switch to the right board. So I forgot this was part number 2, now part number 3. Okay, let me start with some okay, assume that yeah, let's suppose that I have a measurable space. So let X with some sigma algebra A of measurable sets, and the measure mu. So this is my measure, right? I forgot, it's called measure space, yeah?
Yep.
Then okay, I think that I will just define the ergodic transformations, and then we will simply just start with some ergodic group actions on some spaces. Okay, so we say that a continuous map. Okay, it's actually for us, it's, yeah, let me start with the definition. So a measurable map T from X to X is said to preserve mu, so it preserves the measure mu. If the measure of T, say, inverse of E is equal to the measure of E for every E sitting in this sigma algebra A. All right. Then map T preserving mu is said to be ergodic. Okay, so mu preserving map T is ergodic if the fact that E is invariant, so if the fact that some set E is invariant under T implies that this set E is either of the full measure or of the zero measure. So if T of E is E implies that the measure of E is zero or the measure of X minus E is zero. I think I will just state one nice reformulation for ergodicity, probably in terms of just invariant functions, and I think this is going to be enough. Again, so it's ergodic if, let me use, so if this, right, implies that either we have this or this, yeah? Then the following proposition holds. Now let it be the space with finite measure or probability measure. So let mu be a probability measure on X. Then T from X to X is ergodic if and only if. So if and only if almost every invariant function is constant. Well, again, mu almost everywhere. So I should write that if and only if mu almost every T invariant function f from X to R is actually constant mu almost everywhere. This formulation is actually pretty useful. I forgot how is it proved, but I think that the proof is, yeah, one can subdivide one can consider the spaces such that okay, so basically one can subdivide the real line into the segments from, so the proof goes, okay, proof is based on the subdivision, right? Okay, on the partition of R into segments K over to the 2 to the power of n. So from K over 2 to the power of n times 2K plus 1 over 2 to the power of n, as I remember, and analyzing and on the analysis of their preimages.
Speak of we define U almost ever functions. Like, what is the measure on the space of functions? Actually, wonder if it's like it's actually just every t invariant function is constant. So there are
Yeah, in fact, probably every. No, well, you probably. Yes, okay, I agree. Maybe this is. Yeah, unfortunately, I didn't take my notes with this specific proposition. Probably, yeah. I think that every again, since if I take some measure on, say, yeah, L1 or L2, it's going to be, yeah, in fact, I guess that for every function. So how should I prove it? I consider the set of x, say, x of I don't know, sub k comma n.
preimage of that.
Yeah, look at
It's
the
going to be that's because the map is t invariant. That's
yeah. Actually, I didn't say it should be. Yeah, it should be mu measurable function.
Yes.
Yeah, thanks for the question. Yeah, actually, it is. I messed some things up. Yeah, T
Yep.
invariant, and this is very important. It should be mu measurable. Mu measurable means that the preimage of well, the measurable. Okay, the preimage of this is something sitting in my sigma algebra here, right? So, yeah, that's for every t invariant measurable function. Okay, sorry, every t invariant measurable function is constant almost everywhere. So how do we prove it? We consider this intervals and their preimages. We use that it's measurable, then it's going to be good. Then we so basically we use then ergodicity. Oh yeah, all right. Yeah, so
Yeah. So ergodicity,
Yeah.
each of those preimages should be
okay, so we can define
t
like x k sub n as like f inverse of k over 2n k plus n over 2 to the power of n, right? And this belongs to my sigma algebra A. Then I use the fact that if these are constant, then I just get that T is ergodic since the measure. Right, so if it is constant almost everywhere, then what I get?
T of this set xkn will be equal to itself because the function is
Yeah.
right?
Yes,
So
because the
you're gonna
function
see
T
tells
invariant.
us that
Yes. So T of kxn T of kxkn if since f is T invariant, right? Yeah, but this is one implication. Probably the converse is probably.
product. This is true. Would you just use the indicator function?
Yeah, exactly. I think that for so if the inverse of E is equal to E, then just consider F being equal to the indicator of E, right? Is definitely going to be, yeah, so since it is,
T invariant.
yeah,
It's not almost everywhere constant.
so it is T invariant, well, and
It's almost everywhere constant. if
Yeah.
only if the function is asymptotic sets.
okay, so it's mu almost everywhere is equal to 1, right? This is okay. This is which direction? Yeah, well, in this, so this is from right to left, right, and here. So this is mu almost everywhere is equal to 1, and thus it means that the measure of E is equal to 1. Yeah. All right. Yeah, well, here the proof is a little bit more complicated, but one needs to show that actually, yeah, so these are measurable, and we are going, yeah, we're basically going to show that ergodicity implies that the function is almost everywhere constant. Since the problem is that if it is not, then we can obtain probably just by taking the union. Wait, no. Yeah.
Show that this is going to not be a null set for most.
Yes.
Okay.
Yes.
And then you look at those non-null sets and their intersections on them.
Yeah. You need to basically we will need to take the intersections by all k and n, and we will obtain something which is not of the full or zero measure. Yeah. Okay.
Right. Calculates.
Yeah. All right. Yeah, so I think that I wanted to just say just a couple of words about the group actions, and that's it. Okay, so now H act on, so H, a group, act on this space with some measure, and where X is a measure space, such that mu, the measure mu, is H invariant. It is quite simple to find plenty of examples of this, right? Like which fall under this description. So for instance, if you have a Lebesgue measure and you have I don't know, an isometry group, full isometry group acting in the space X, right? By isometries, you definitely get a measure which is invariant under your isometries. And yeah, and then we say that then again, H, the action on X, is ergodic if every, right, if every H, which definitely acts as a map from X to X, is ergodic. And for probability measures, it is equivalent to the fact that, so this is equivalent to okay, for probability measures, this is equivalent to that every H invariant function okay, this mu almost everywhere constant, right? Or this is equivalent also. So by definition, I can say that I have an invariant set, right? So H U is equal to U implies so if HU equals U implies that the measure of U is 0 or the measure of X minus U is 0, since definitely I can translate it to every element, right? Okay.
Like, I mean, you could take a free group on two elements where one thing maps to something non-ergodic and the other thing maps to something that is ergodic. Free group of two elements acts in a circle, one by irrational rotation, one by irrational rotation.
You mean that not every ergodic is covered by this?
Because it's the last condition, right? Because it's possible that you have a group where there are ergodic elements, but there are also non-ergodic elements, right? But your definition of an ergodic action is that every non-trivial element acts by an ergodic transformation.
Yes.
Like I could take an action of a free group on two elements where one
Yeah.
generator goes to something ergodic and the other generator goes to something periodic, let's say.
Okay, so this means that
You could do the condition by saying
yeah, for some element H,
for
yeah.
for all of H, yeah.
Okay, so if for H in H we have HU equals U, right? Then
We say not trivial, but yeah, the map's not ergodic, but
okay, yeah, the identity maps are not ergodic.
that's
So probably I should say that not trivial, yeah. Okay, yeah, thanks for it was actually good since otherwise, yeah, I did want just this. Otherwise, it would be just really very strong condition. Okay, so in fact, yeah, it's now time to finish the lecture. So what's the plan for the next lecture? We will discuss a little bit more the properties of ergodic actions of groups on probability spaces. Our spaces, I can just like, I can give a spoiler that we will consider the spaces with finite measures since we consider lattices. Lattices give us finite quotients like G mod gamma and something. So we have, in all these cases, we will mostly deal with spaces with finite measures. So all this in particular, this reformulation in terms of invariant functions is good. So then we will sketch. So basically, I hope to sketch the proof of the most of rigidity theorem just next lecture, and it is going to be based on these properties of ergodic actions of groups. Okay, yeah, thank you for your attention, and thank you for asking good questions and making comments. Okay.